This activity walks you through establishing what are called the three geometric mean relationships. The geometric mean relationships are found in a unique diagram, which is a large right triangle with the altitude drawn from that right triangle to the opposite side. Why does it have to be this diagram? Why is something unique found in here? Well, what happens is that inside the big triangle there are forming new smaller triangles, and they happen to be similar with each other. Now, because of that, it creates proportions, and these proportions are quite unique. And the reason they're quite unique is that they use a side more than once. You'll see what I mean. So here's the original diagram. I'm going to call the red one the left and the green one the right, and of course the big one the whole one. If I compare the little one on the left to the whole one, I can establish that they must be similar. How? They each have a right angle, and they each share angle A. AA. They're similar. Now watch what happens when you begin to pair up the sides proportionally. If I use AB here, that's the hypotenuse, and it would compare to AC here. If I use AD here, that's the side with the angle and the right angle, AD, it would match up with AB in this one. Notice something unique happened. The AB length gets used as a numerator in one case, a denominator in the other case, because in one case AB is a hypotenuse, but in the other triangle AB is the shorter leg, at least in this diagram. Interesting. The fact that you get the same value as the numerator as well as the denominator in the proportion creates what's called the geometric mean. That the side AB squared is AD times AC. Let's take a look if we compare the right to the entire. They are also similar by AA because I have an angle. Let's see, it's actually angle C is in common, reflexive. And then I have the right angle. So these are also similar. These were similar and these were similar. And I can do the same thing. I can say BC in the large one matches up with DC in the right one. And then I can then say AC, this hypotenuse, matches up with the hypotenuse BC there. Once again, do you notice that BC is repeated? Once as a numerator and once as a denominator. We can cross multiply and obtain what is known as the geometric mean, a new one, a new relationship. Finally, we could also compare the two little pieces. Now there's no common angle to compare them. They both have a right angle. You can go about this two different ways. You can realize that if this angle has a dot, because in the original whole one, a 90, a dot, what would be left is the x. You can discuss kind of the idea that those third angles have to work out the way they do it. Or you can use a transitive argument that the little one's similar to the big one. Sorry, the left one is to the big one. The right one is to the big one. So transitively, they have to be similar to each other because they're both similar to the whole together. And so they have to be. Now this also creates a relationship. I could pick BD from the left one, and it would correspond to DC. I could pick AD from the left one, and it would correspond to BD. Notice once again, BD in this case gets duplicated once in the numerator, once in the denominator. BD squared equals AD times DC. also a geometric mean relationship. Now there's more to discuss, but that's not the goal of this video. I wanted you to understand the relationship, the uniqueness of this. These three cool little relationships are found all through similarity and proportions, and they're not that hard to discover.